So we're going to be talking about stoichiometry today. How many people at some level have done stoichiometry? Okay. So to me, the word itself is more complicated than the concept. When you first look at it, it seems hard, but when you really break it down and what you have to do, it's not that bad. And there's a set formula that you're going to follow, and when you do that, you're going to get your answer. Okay? So what stoichiometry is it deals with comparing amounts of one thing in your reaction to amounts of another thing. And so imagine we have a reaction A plus B yields some products. You can use stoichiometry to compare amounts of two reactants together. Say if I have 5 grams of reactant A, how many grams of reactant B do I need to react with it? You can figure out, based on how much reactant you have, how much product you can make. You can say, you can go product to product. If I'm getting 2 products and I know how much of one that I get, how much of the other one must I have got? Another way to look at it is you can go backwards. You can say, if I need 10 grams of product, how much of each reactant do I need to start with? And when we talk about amounts, we're going to be dealing with both moles and grams. And so last week, we learned how to go back and forth between moles and grams. We're going to extend that out. And so what this allows us to do is we can go from moles to moles. And when I say moles to moles, what I mean is moles of one thing to moles of another thing. Let me So what we're going to do is if we look at a reaction, we are going to assign which thing it is that we're starting our conversion with. It is the thing that we know how much we have, and we're going to call that thing A. It doesn't matter which it is. It could be any of these 3, but we're going to say that's A. If we know how many grams of A we have, we're going to start at this spot. And then if we start here, we can go to here, here, or there. But we have to go one step at a time. Going from here to here is what you already know how to do. From grams of A to moles of A. It says you're going to use the molar mass to go from grams of A to moles of A. So we can go from grams of A to moles of A, grams of A to moles of B, B being the thing you're trying to figure out how much you have or how much you need. Or you can go all the way to the end from grams of A to grams of B. So in terms of stoichiometry problems, we have 4 types. We can go moles to moles. We can start here and go to there. We can go grams to moles, moles to grams, or the whole thing, grams to grams. And the way this works out is we're going to do it with dimensional analysis. And up here in this corner, I have essentially your template for all of these problems. This is not on the cheat sheet, and so if you like to use this, make sure you have it memorized for the exam or whatever you need it for. Okay? So what this says is X grams of A. So this is the full thing, assuming we're going grams to grams. And so if you're not going grams to grams, you're just going to use part of it. You're going to start here, or you're going to start here, and you're going to end here or here, depending on the specific problem. So you're just going to erase the part that you don't need. So what this says X grams of A, meaning X is however many grams you're starting with, what the problem tells you you're starting with. So you plug that in for X. On the bottom, it says molecular weight grams of A. And on top, it says 1 mole of A. And so A, you'll have to figure out what A is. The grams are your unit, and the number that's going to go there is just the molecular weight of whatever A is. if A is hydrogen, H2, the molecular weight would just be 2. And then you'll have 1 mole of A always on the top. So then this says coefficient, COEF, of B, coefficient of A. You're just going to pluck those right out of the reaction. What is the coefficient on A and B? If this is A and that's B, the coefficient on A is 2, the coefficient on B is 1. You'll just stick those numbers in, and then you'll always have 1 mole of B on the bottom here, and then molecular weight, whatever that is, grams of B. And we're going to do examples of all of these, so you'll see how to plug these in. But essentially, all you have to do is put in whatever you're starting with, whatever the molecular weight of A is, the molecular weight of B, and then pull the coefficients out of the reaction. It's not that hard. It's the same thing over and over and over again. So this is a mole to mole. So in this case, we're going to use the mole ratio that we talked about on that first question. And this just comes from the coefficients in our reaction. So in this reaction up here, the mole ratio is 5:1 for oxygen to C3H8. Because oxygen has a 5 for the coefficient, C3H8 has a 1. So it's just a 5:1 mole ratio. That mole ratio is a conversion factor. That conversion factor right there. Remember when we were using dimensional analysis for conversions, top and the bottom were equal to each other. That was our conversion factor. This is telling us that 5 moles of oxygen is equal to 1 mole of C3H8. That's what that's telling us. So, in this case, we're starting with 0.40 moles of C3H8. And we need to figure out how many moles of oxygen we need to react with it. So in this case, C3H8 is our A, and oxygen is our B. We're starting with the C3H8, so that is our A. We're going to oxygen, so that is our B. So because we already know moles, we're going to start at this spot. We're going to ignore this over here. So because we're starting here, that's not going to be a 1, that's going to be our 0.4. So I'm going to put 0.40 moles of C3H8. And then this tells me, down here, these are moles. Based on this and that, I know I have to have moles of A, and A was C3H8. But just like before, that unit went down there. On the top, I need to have moles of B. We're going to oxygen, so I need moles of oxygen. The numbers that go here are the coefficients on those things. And so I just pull them out of the reaction. Oxygen was 5, C3H8 was 1. This is a mole to mole conversion. We're just going to moles of oxygen. So we need to have moles of oxygen in the top right corner of our grid, which we do. And so we're doing a one-step stoichiometry problem. We're just going from this one to that one, and we're done. So if we do that math, it comes out to be 2.0 moles of oxygen. Just do the math just like you've been doing your dimensional analysis, and you're done. That is a mole to mole conversion. It's as easy as it could be. So here's another one. We're going to burn some benzene. The reaction is given up there. First question is, what is the mole ratio of oxygen to benzene, which is C6H6?
15 to 2.
Yes. 15 to 2. Oxygen has a 15, benzene has a 2. Next question is, how many moles of oxygen do we need to react with each mole of benzene? And this is, we can do this on the board, which we will, but you can also do this in your head in thinking about what these coefficients mean. This means that 2 moles of benzene requires 15 moles of oxygen. That's what those coefficients mean. So if you only have 1 mole of benzene, how many moles of oxygen do you need?
7.5.
7.5. Half of that. 2 of these requires 15 of those. If you only have 1 of these, you have half as much as the recipe calls for, and so you only need half of your 15. So 7.5. We can also do it exactly how we did it with our dimensional analysis. We have 1 mole of C3H, wrong thing, C6H6, moles of C6H6, moles of oxygen. These are just the coefficients. This is 15, and that is 2. That comes out to be 15 divided by 2, which is half of 15, 7.5 moles of oxygen. You can go the other way also, though. You don't have to start with benzene and figure out oxygen. That's the same thing, isn't it? Yeah, I read it backwards. So we're just changing it up. So in this case, we have an odd number. It's a weird number. It's not 1. With a 1, we could look up there and say, well, 1 is half of that, and so I need half of that, which is 7.5. But 0.38, you can't do that. But when you use it this way, nothing is more difficult. It is exactly the same difficult. You just replace 1 with 0.38 mole of C6H6. This is going to stay the same because the coefficients didn't change. And so apparently when you do that, it comes out to be 2.9 moles of oxygen. Is everybody comfortable with this? Because it's just going to get bigger from here. So if you can't do this, we need to fix that. Because this is going to be included in every single stoichiometry problem. Okay. So here's another one. What is the mole ratio of CO2 to oxygen? 3 to 5. CO2 has a 3, oxygen has a 5. And so in these questions, we were figuring out if I have so much of one reactant, how much of the other reactant do I need? This one, it says if I have 2.3 moles of oxygen, how much carbon dioxide am I going to make? Now we're going from a reactant to a product, but nothing in our process changes. When you're doing stoichiometry, whether it is a reactant or a product, doesn't matter one bit. And so we're starting with 2.3 moles of oxygen. So I'll have moles of oxygen, moles of CO2. Oxygen was 5, CO2 is 3. So we're done. Comes out to be 1.4 moles of CO2. And that's it. So here we're working backwards. We're saying we need to make 0.62 moles of aluminum chloride. How many moles of chlorine do we need to react in order to get that? This is more along the lines of the type of problem you would do in a lab. You don't go into a lab and say, well, I have this much on the shelf of my reactant, how much can I make? You have a need for that product. You say, I need to have 0.62 moles of aluminum chloride. Okay, if I need that much, how much reactant do I need? If I don't have that much, I need to order some more. Your product is what you're really going for. The reactants are just what you use to get there. But even though we're going backwards, again, our process is not going to change. We have 0.62 moles of aluminum chloride. Moles chloride. Chlorine is 3. Aluminum chloride is 2. And that's all we have to do. It comes out to be 0.9. So now we're going to move on to grams to moles. So grams to moles is essentially going to take what we just did and it's going to tack one step on to the beginning. And that step that you're going to tack on is the grams to moles conversion that we did last week. So with the problems we just did, we were going from here to here. In grams to moles, we're going to go from here to here. And so we're going to start with however many grams of A, that's going to go there. If you're starting here, that number is going to be a 1, always. So then all we need to do is calculate the molecular weight of A, use our coefficients, and we're done. In this case, we're not using this part yet. We're going from here to here. So this one says we have 80 grams of oxygen that were produced. How many moles of potassium chlorate decomposed to make our 80 grams of oxygen? So I'm going to start with my 80 grams of oxygen. That's the only thing that I have available to start with. So I'm in the top left corner. My X is 80, and then I have grams. My A is O2. So this says down here I need to have the molecular weight, grams of A is oxygen. Then on top I have 1 mole of A, and A is oxygen. So what is the molecular weight of O2?
32.
Careful. I heard 32, I heard 16.
32 because it's 2
It's
oxygen.
32 because it's O2. There are 2 oxygens, each one is 16, so it's 32. Now we have one more step to go, but it's just the coefficient. And so we have moles of O2, and on top we have moles of KClO3. KClO3 has a 2, oxygen has a 3. We're done setting it up. All we have to do is the math. Yes?
Where do we get 32 again?
32 is the molecular weight of oxygen O2. So each oxygen weighs 16 based on the periodic table. There are 2 of them, so 16 times 2 is 32. Does that make sense?
Yeah.
It's also 16 plus 16. So it looks like I don't have the answer up here. Can somebody do this for me? Say it again. 2.5 moles of that? 2.5?
1.66666.
1.6?
Yep.
1.6?
Repeat it, yeah.
Okay. So we had 366, so 1.6. But what this is pointing out is knowing how many moles of potassium chlorate decomposed is not really useful to us whatsoever. Because if somebody says 1.5 moles of potassium chlorate, you'd have no idea, I have no idea how much that is. In order to figure out how much that is, we're going to figure out, well, the molar mass of potassium chlorate is this, and so 1.5 moles is X grams. We know how much a gram is. The more we work in lab, the more comfortable we get with masses and knowing how much that is. And so grams to moles, and anything with moles in our stoichiometry, is not the type of problem you would be doing in lab. You're going to be working with grams because you know how much of something you need in grams. And we don't have a scale that measures in moles. Scale measures in grams. So both the input and the output have to be grams. Important to remember what this is pointing out. This is something that people like to get wrong. These numbers only deal with moles, not grams. Sometimes people will try to skip this and they'll say, well, these two have the same coefficient on them, and so if I have 10 grams of that, I get 10 grams of that. It doesn't work that way. You can't say 10 grams of that is 15 grams of that because the 3 is 1.5 times that big. The balanced equation, meaning the coefficients, only tell us about moles, not masses. And so what we need to do is tack on the last step here. It's essentially the reverse of this. We're going to go from moles to grams. And that's another thing that we did last week. Last week we went from grams to moles. We also went from moles to grams. The reason this gets big and confusing is because the only conversion factor we have between A and B is moles. Even though moles aren't a practical thing to work with, we have to convert 2 moles before we can use our conversion factor. And then once we use our conversion factor, we have to go back to grams in order to get back to real life. So before we do the whole thing, grams to grams, we still have this partial problem that we can do. We can go from moles of A to grams of B. So we have our same reaction there, our potassium chlorate decomposing. And so it says 1.5 moles of potassium chlorate is going to decompose. And it wants us to figure out how many grams of oxygen is going to be produced when 1.5 moles of potassium chlorate decomposes. So in this case, we are starting here with moles of A. And so if we start here, down here, this is not going to be anything. We can skip the molecular weight grams of A part. So we move on to here. We just have our coefficients. So I'm going to have moles of potassium chlorate on the bottom. We're trying to go to oxygen. So I'm going to have moles of oxygen on the top. These are just coefficients. Oxygen is 3. Potassium chlorate is 2. But we're not done, because we have moles in the top right corner and we need grams. So we need to do the last step up there. On the bottom, it says I'm going to have 1 mole of B, and B in this case is our O2. On the top is the molecular weight grams of B. So I have grams of B, which is oxygen. What is the molecular weight of oxygen? 32. If you do that math, you'll get something. I hope you get something. If you don't, you might want to replace your batteries. Grams of oxygen. Is everybody comfortable with this one? The moles to grams. So now we've done moles to moles, we've done grams to moles to grams. The only thing left is grams to grams. It's everything that you've done. You're just going to have to put all the steps together. So it's not more complicated. I always tell people that all stoichiometry problems are the same difficulty. It's just some of them require more work. Because it's not hard to do this. It's just how many lines do you have to draw, how many buttons do you have to push on your calculator. And so the last thing we need to do is grams to grams or mass to mass. So there is the reaction that we're going to be dealing with for this one. We're just making sodium chloride. This question says we need to make 9.2, we have 9.2 grams of sodium. That is how much we have in our lab. And we know that we want to react all of it. And so how much chlorine gas do we need in order to completely react our sodium? So we're going to start with 9.2 grams of sodium. We're up here, top left corner. So I have grams of sodium, moles of sodium. What number goes there? 1. If you're starting with grams, that number will always be a 1. And what goes down here? The molecular weight of sodium, which is 23, I believe. 23 grams of sodium. Now I've got moles of sodium to moles of chlorine. What number goes here? 1. Chlorine is a 1. Sodium is a 2. I've got moles of chlorine to grams of chlorine. This one's the easier of the two. What number goes here? 1. That will always be a 1. There will never be a stoichiometry problem where that is not a 1. So we've got 1. What number goes up here?
Times 2, so 70.
35.5 times 2 is 71. A lot of them I like to round, but a lot of them are very close to a whole number. Chlorine is an exception. It's very, very close to 35.5. And so I would not round chlorine to 35. I would keep it 35.5. That times 2 is 71. That is big old step by step of what we just did. And then in the end, it comes out to be 14.2 grams of chlorine. So here, we're going to take it another step. We're going to think about it. It says what mass of sodium chloride should be produced when 9.2 grams of sodium reacts with 14.2 grams of chlorine. This is hinting at a type of problem that you're going to have to do coming up called the limit reactant problem, where you're going to have, you have this much of reactant A, this much of reactant B. You don't know how they really compare to each other. How much, if you mix them together, how much product can you make? In those cases, you don't know which one you have more of. In this case, though, we just calculated that 9.2 grams of sodium perfectly reacts with 14.2 grams of chlorine. That is exactly how much is needed to react together. So in this case, we can just pick one. We can say, we're going to start with 9.2 grams of sodium and figure out how many grams of sodium chloride we can make. So right below it, I'm going to start again with 9.2 grams of sodium. So the first couple steps are going to be identical because it's still sodium. Once you get up here, though, it's going to change. A stayed the same, so anything with an A is not going to change. But what our B represents did change. What is B now?
Sodium chloride.
It's sodium chloride. And so now I'm going to have moles of sodium chloride, and sodium chloride is a 2. And so up here I had a 1, now I have a 2. And so my math has changed. And as I go forward, it's going to continue to change. I'm going to have 1 mole of sodium chloride down here, but now I'm going to have grams of sodium chloride. So that comes out to be 58.5. 58.5, I think. So 58.5 is going to go there. And that works out to be 23.4 grams of sodium chloride. So the difficulty here was exactly the same as difficulty here. All we had to do was figure out what is A, what is B, and then are we starting here or here, and are we ending here or here? In this case, we went from here to here. Question? So what this is showing is if you did the math again, but instead of starting with that, you started with that, the 14.2 grams of chlorine, and you do the math, you get the same exact answer, which is what we predicted and which is what we knew because we said that exactly reacts with that. And so if they react together, they're going to make one product, and so they're going to make the same amount of product. Just are you looking from the left or are you looking from the right? This is pointing out something called the conservation of mass. When we talked about balancing equations, we said that you have to start and end with the same number of atoms of each element. And each atom weighs a certain amount. And so if you figure it out, what that means is if you start with a certain amount of mass in your reactants, your products have to equal that same amount. You cannot create or destroy mass in a CHM1030 lab. You just can't do it. No matter how much you try, it's not going to happen. Okay?
That's why I was wondering. I was like, we didn't really have to do all of that work. We just added them together.
Right, right. And so, because if you know that, there's only one product. And so all of our starting mass has to end up in that one product. There's no other place it can go. And so what she's noticed is 9.2 plus 14.2 is 23.4. If there were two products, then that doesn't work. Because yes, you know the mass of the two products combined will be 23.4, but you wouldn't know how that mass was distributed between those two. You would have to do the stoichiometry in order to figure that out. This is what that looks like. This is this reaction. We have our sodium metal reacting with chlorine gas, And believe it or not, that shiny, soft, metal, clay-looking stuff, plus that yellow gas that will kill you in an instant, together makes salt. That you eat all the time, and that is a big part of what you as a human being are. And that's what we're going to do, is going to change scales. Instead of talking about common real life, we're going to deal with scientific real life. So this is the space shuttle, before they shut it down. It says when they lift off the space shuttle, one of the fuels that they use is hydrogen. Hydrogen is the fuel. And so it says to get the space shuttle into space, it takes 1.8 times 10 to the 8 grams of hydrogen. It's 180 million grams of hydrogen. So we have to figure out, if we burn 1.8 times 10 to the 8 grams of hydrogen, how much oxygen is going to be consumed? So you have the space shuttle. It's burning all this hydrogen. Where is the oxygen coming from? The air. I guess I think it's coming from the air. I don't know enough about space shuttle to know if they have oxygen tanks as well. We're going to assume it comes from the air. So all of this air is coming out, so all this oxygen is coming out of the air. We have to figure out how much that is, and it's going to be a very large number. If we do our calculations, and we don't get a gigantic number, we know we did something wrong. And so it says what mass of oxygen gas is consumed, how much oxygen is going to react, and then when you do that, how much water vapor is produced. If you've ever seen a space shuttle take off, whether it's on TV or in person, what comes out the back of that space shuttle? Well, it looks like there's a giant cloud, right? That's steam. That is the water vapor that's being produced. So because it's burning, it's very hot. When it's made, it's water vapor, it's gas. But as soon as it touches the atmosphere, it cools down, and it condenses, and it turns into a giant cloud. So we need to figure out how much oxygen gas we're going to consume, and then how much water that is going to be. So we are starting with 1.8 times 10 to the 8th grams of hydrogen. We're starting here. We need to get the mass of oxygen, so we need to go all the way down to here. Grams of hydrogen, moles of hydrogen. What number goes here?
1,
1. What number goes here?
2.
I'll cut it to 2. Hydrogen is essentially 1. There's 2 of them, so it's 2. Now we've got moles of hydrogen, the moles of oxygen. Oxygen is a 1. Hydrogen is a 2. Moles of oxygen, grams of oxygen. What number goes here?
32.
32 and
4 moles.
1. So if you do that, what do you get?
You ready? 1, 4, 2, 5, 7, 4, 2, 5, 7, 4.
Is it not giving it to you in scientific notation?
No.
It's not.
1.4 times 10 to the 9th.
0.42 times 10 to the 9th grams of oxygen. Does that number make sense? We said we expected a gigantic number. That's a pretty gigantic number. It is bigger than the number that we started with. I mean, it could still be gigantic, but smaller than the number we started with. So does it make sense that it is larger than the number we started with?
Yes, because oxygen weighs more than hydrogen.
Correct. Oxygen weighs more than hydrogen. And so you would expect the amount of oxygen to weigh more. That, though, you have to be careful with that assumption, because that also depends on the coefficients.
Yeah, it's 2 and 2, so that's why it would make
It's not 2 to 2.
It's 2 to
It's
1.
2 to 1.
That makes oxygen bigger.
And so,
It
well,
requires
it's actually
more
going to make oxygen smaller. You require 1 oxygen molecule for every 2 hydrogens.
Still, 4.04 is a heck of a lot smaller than 16.
Right.
Or 32.
Right. And so the mole ratio it's a half, right? You have half as much oxygen molecules as hydrogen, but the mass difference between them is a whole lot larger than a 2-fold difference. And so that more than makes up for that. So yes, it makes sense that that number is larger than that one. Now, let's do water vapor. There are 2 ways we can do water vapor. How do you want, actually there are 3 ways we can do water vapor. How do you want to calculate how much water vapor we made?
Add up 2 numbers.
Maybe the easiest one is add the 2 up. We now know how much hydrogen we have, how much oxygen we have. We're only making 1 product. All of that mass must go into that water. So we can just add them together. If you do that, what do you get? That's going to be 1.60. 1.60. 0.60 times 10 to the 9th grams of water. That's just adding the 2 together. So hopefully, if we do it this way, we get that same number. Doing it the long way, though, we have our choice of where we want to start with. Because now we know how much hydrogen. We also know how much oxygen. So we can start with either one of them in the top left corner. And they're going to give us the same answer. My suggestion, let's do hydrogen, because we already worked half the problem out with hydrogen. This is where the problem changes. Right here, instead of oxygen, I need water, and water is a 2. Water is 18 grams. So you put that in your calculator, hopefully you get that same number. So that was this. That's the slide showing what we did there. And here is what we just did here. And this does in fact show 1.6 times 10 to the 9 grams of water. And so we did not break the rules of the universe by destroying matter or making matter. And so we are... We're now going to take this and we're going to add a little bit of thought to it. Not a whole lot, just a little bit. So, is there anyone that is not comfortable doing this? Okay. So, like I said, in a limiting reactant problem, we're going to have a certain amount of one reactant reacting with another amount of our other reactant. And they're not going to equally even react with each other. Okay, they're not custom made to react with each other. We don't know which one we have more of. And so when you react them together, one of them is going to run out before the other one does. And so we say that one, how much you had of that one, limits how much product you can make. Because when you run out of one reactant, you stop making product. And so if sodium runs out, sodium limited how much product you can make. And so we say sodium is your limiting reactant. And so a problem is going to say you have this amount, this many grams of A, this many grams of B, which one is the limiting reactant? And you're going to have to figure that out. So let's look at these pictures down here. What this is just magnesium, just like we burned, and we're putting it into acid, either hydrochloric or sulfuric acid. They'll both do the same thing. We'll do this in lab coming up. So let's just look at A. Let's say this is what it looks like when you drop the magnesium into your acid. So we have a beaker of acid, magnesium is sitting at the bottom, and there's a bunch of bubbles coming off. If that happens, and then it stops reacting, and what you have is beaker B. Which do you think is the limiting reactant, the magnesium or the acid?
Acid.
Why the acid?
Because you wouldn't have the rest of the magnesium metal involved.
Correct. And so, because the acid is dissolved in water and it's clear, you have no way of knowing whether that's actually gone or not. You can't see it, right? But what you can see is that the magnesium is not gone. Magnesium is not gone, yet it stopped reacting. And so you can infer that the acid must be gone. If the acid is gone, that's the limiting reactant. If you look at it, what is gone in the product side, after the reaction is finished, it was the limiting reactant. The thing that is left over, we say, was in excess. We had an excess amount of it. We had too much of it. We had more than we needed. And so some of it is left over. What about beaker C? Which one was our limiting reactant? The magnesium was our limiting reactant. It is gone. And so we assume that the acid is left over even though we can't see it. So the magnesium in that case was our limiting reactant. Our acid was our excess reactant. That's what we said. That's what we also said. So let's look at this picture. This is a nail in a solution of copper chloride. Looking at this picture over here, which do you think, this is before and after, what do you think is the limiting reactant? The iron nail or the copper in the solution? The copper in the solution. How did you know? Just clearly nail left, right? How else could you figure that out? It's not blue anymore. It looks to me like they took their picture about 5 minutes too early, that there's still a little bit of blue left, but clearly the blue is essentially gone. And so in this case, the copper is going to be the limiting reactant. Even if you let this go, it's obvious you're not going to eat up all of that nail. And so even though it hasn't run out yet, it's clear that the copper is what's going to run out. So this works just like anything in real life. You know you need X number of pieces that go together to make what you want to make. So if we're making a solar car, to make our car, we need a body, a solar cell, a motor, 4 wheels. You put those together and you've got a car. This is just like a chemical reaction. A plus B plus C plus D, 4 reactants yield 1 product. It's a synthesis reaction. So if that is how it works, and these are the parts that we have, how many cars can you make?
3.
Why 3? You got 3 sets of wheels, right? You've got 4 bodies, 5 solar panels, 6 motors, but you only got 3 wheels. Now a real engineer would say, let's just make a tricycle. But we're chemists, not engineers. And so we can't think like that. We only deal with what the reactant tells us. Because in chemistry, if you change this, it's not the same reaction anymore. A 3-wheeled car works the same as a 4-wheeled car, but sodium chloride does not work the same as calcium chloride. They're different things. Let's look at another one. Here, we've got it drawn out as molecules. Okay? So this tells us that 2 hydrogens react with 1 oxygen to make 2 waters. So if this is what we're starting with, and you were going to draw what the product looked like, what would you draw on the right-hand side, and how many of each would there be?
Three water molecules.
You got. So how many hydrogens do we have? Hydrogens are the white ones. We've got 1, 2, 3, 4, 5, 6, 7. We have 8 hydrogens. I'm just going to write that down. We have 8 hydrogens. How many oxygens do we have? 3 oxygens. How many waters are we starting with? None, right? And so we have to figure out, okay, we take these together, we react them, what are we going to end up with? So it says, for every 2 hydrogens, we get 2 waters. Which also means for every 1 hydrogen, we get 1 water, right? So we have 8 hydrogens. So theoretically, that could make 8 waters. Because it's for every 1 hydrogen, you can make 1 water. Because each hydrogen is H2, and it takes 2 hydrogens to go into a water. So you essentially take that, stick an oxygen on, and you got water. Our oxygens, though, are not a 1-to-1 ratio. This says for every oxygen you have, you can make 2 waters. So based on simply how many oxygens we're starting with, how many waters can we make? 6. The oxygens say we can make 6 waters. Even though we have enough hydrogen to make 8, we only have enough oxygen to make 6. So we can only make 6. And so when we finish, what we're going to have is we're going to have 6 waters. What else are we going to have, though? We're going to have 2 of these left. So I'm not going to attempt to draw it. I think there's a picture. Nope, there's not. But I think you can, the way my handwriting is, I think you can understand my handwriting better than my drawing. And so you would have 6 of the waters, and a water, if hydrogen is white, oxygen is red, you'd have that. You'd have 6 of those, and then you'd have 2 of these H2s also flying around. That is your excess reactant. Your oxygen was your limiting reactant. So this slide has a lot of text on it. Okay? This is the steps that we're going to use in order to figure out our limiting reactant in a math problem, the type of problem that you would see on a quiz or an exam. There are 2 ways to do these problems. We are only going to do one of them in class. The other one requires some logic that I find students don't necessarily always get correct. The way we're going to do it, if you do the work, you get the right answer. There's no interpretation involved, okay? You'll do the math, you'll get 2 numbers, and everyone can say, of these 2 numbers, which one is the smaller of the 2? That you can do. The method we're not going to cover, a method that you might have covered in another class, a method that you might come up with yourself, when you get 2 numbers at the end, you have to think, okay, what does that mean? It's not which one is smaller, it's what does that mean? And if you can figure that out, sometimes it'll save you a little bit of work. But if you're not comfortable doing that, the way we're going to do it is always going to give you the right answer. And also, the way we're going to do it leads to the next part of the problem. So usually when you see this, it's going to say, part A, what is the limiting reactant? Part B, how much product can you make? So the way we're going to do it you're going to solve both problems at the same time. So you're going to have the answer for B, all you have to do is copy it down, or draw an arrow, or write C letter A, or something like that. If you do it the other way, you find A, and then you have to find B. And so if you have a two-part problem like that, the logical way doesn't save any work. And so you might as well do it the foolproof way. Okay? And so this is the way we're not going to do it. This is if you have X amount of A, Y amount of B, compare them to each other and figure out, do I have more of A than I need? Do I have less of A than I need? Or do they match exactly? But you have to think, how much do I need? And then compare that to what you actually have. So this is not what we're going to do. And so, in this example here, I'm going to show you the way that we are going to do it. And so here, this is an example of a limiting reactance problem. You're going to have the reaction written out for you. You always want to make sure that it's balanced before you use it, but unless it says it's unbalanced, most likely it is balanced. Okay? And so it says, what is the limiting reactant when these two sets of reactants are mixed together? And so part A is half a mole of P4 and 5 moles of oxygen. In order to find a limiting reactant, you can find amount of product as moles or grams. Because an exam problem will almost always have part B, how many grams can you make, my suggestion is to just find grams in part A. Then you've already finished it, you're done with the whole thing at once. So what we're going to do is we are going to do a stoichiometry problem with 0.5 moles of P4, figure out how much product we can make, completely ignoring the 5 moles of oxygen. And then we're going to completely ignore this, do a second stoichiometry problem with 5 moles of oxygen, and figure out how much product we can make. Whichever one makes the least amount of product is our limiting reactant. And so let's work this out. Number one, for part A, we've got 0.50 moles of P4. And we're going to take this all the way to grams. Because this problem does not actually ask you for grams, you could just go to moles. But I'm going to get you in the habit of going all the way to grams. And so we need to go from moles of P4 to moles of P2O5. P2O5 is 2, P4 is 1. And then we've got 1 mole P2O5. What's the mass of P2O5? Oxygen. Phosphorus is 31. So 62 plus 16 times 5. 16 times 5 plus
142.
142? Thank you. 142. Now, if we do all of that, well, that's going to actually come up to 142. 42 grams of P2O5. So if you put that all in your calculator, it's going to come out to be 142. 0.5 times 2 is 1, and so the whole thing just goes away. Now we're going to do the same thing down here, but with our 5 moles of oxygen.